In today's lesson, we are going to be looking at rational exponents and radicals. Now, this is going to be a continuation on our power laws that we've been looking at in the previous lessons. So we've already looked at multiplying powers, dividing powers, power of a power, negative exponents, and zero exponent. So those are things that we should have learned, or that we may not maybe should have learned, but things we should have seen in grade 9 and possibly even grade 10. Now, rational exponents and radicals you may have seen before. You've definitely seen radicals before, but maybe you didn't associate it with the terminology that we're going to be using, and you may not have used them in exponent questions. So it will be a little bit new, but you will see some familiar things. So to start off, rational exponents. So here we have a couple examples of rational exponents. X to the power of 1/2, 8 to the power of 1/3, 16 to the power of 3/2. So these are all examples of rational exponents. So hopefully you can make the connection between all three. And by definition, a rational exponent just means that the exponent is a fraction. So that is a rational exponent, where the exponent is a fraction. Now for radicals, these should be a little bit familiar, or at least we've seen them before, hopefully. Definitely should have seen the first one, right? The square root x, or the square root of x. You should have seen that before. So radicals, by definition, they are the opposite of an exponent. So the opposite of an exponent, which makes sense because we've seen the square root before when we've wanted to cancel out squaring, right? You think back to the sum of squares or Pythagorean theorem. You're trying to cancel out that squared, you square root. You think of solving equations. Cancel out the square by square rooting. So radicals are the opposite of an exponent, and it uses the symbol uses that symbol, which is the symbol for the smallest root, which is the square root. Now there are other examples, and in these cases we would put the values in front of the root. So here we see a 3, that means it's the cubed root. You could have the 4th root, the 5th root, the 6th root, and so on. Now these are also called, or also known as roots, because we just mentioned square root, cubed root, 4th root, and so on. So they're also known as roots, but not to be confused with x-intercepts when we're dealing with quadratics. So different meaning when we refer to roots, but we'll mostly refer to them as radicals. So rational exponents law, or the rule when we're dealing with rational exponents and converting between them and radicals. So with a rational exponent, we have a fraction for our exponent. So we'll say it's just any fraction a over b, a numerator and a denominator. Our numerator, the a value, is going to tell us what the exponent on our radical is going to be. Right? Same if our exponent was a whole number, that just tells us the exponent, the power, what we're multiplying it by, or how many times we're multiplying the base by itself. B, the denominator, that tells us what root we're dealing with. So the denominator goes in front of our root symbol, and it's going to tell us what root we're dealing with. So that's all it really takes to convert. We're just taking the numerator and the denominator of our rational exponent and just splitting it up into two parts on our radical. So let's just go through a couple of examples and write each in the rational form. So right now they're written as radicals. I want to convert them and write them as rational exponents. So the value under the root symbol is going to be our base. So in this case we will have x, x raised to the power. It will be a fraction. The overall exponent, the 5, is going to be our numerator. the value in front of our root symbol is going to be the denominator. So the fourth root of x all to the power of 5 is the same thing as saying x to the power of 5 over 4. Next we have 3. We have just the root symbol. So we're missing some pieces of information here. We know our base is going to be 3 because that's underneath the root symbol. But what is our fraction going to be? Well, do we see it raised to an exponent? Do we see a bracket and then a value raised here? We do not. So the only exponent that can exist there, where we don't see it, has to be a 1. So there's an invisible 1 here. Now, what is our denominator? Well, in this case, our denominator has to be in front of our root symbol. Do we see a number there? We do not. So what number would be there? What does this symbol normally indicate? Well, normally we indicate this symbol as the square root. And square root is the opposite of squared, and squared usually implies a power or an exponent of 2. So in this case, if we do not see anything in front of our root, we assume that it is a 2. So no value in front of the means 2. So if we don't have a value in front of that root symbol, it means that it's a 2. It's a square root. So in this case then, the square root of 2 or of 3 can be written in the rational form as 3 to the power of 1/2. For C, similar idea, at least with the exponent. We don't see an exponent, so we assume that there's a 1 there. The base is y. We do see a value in front of the root, so this is the same thing as saying y to the power of 1 over 3. And then lastly for D, 8 is our base. The numerator is 3, that's our exponent. The value in front of the root is 5, so that is our denominator. So this becomes 8 to the power of 3 over 5. And that's how you convert from a radical to a rational form. Next, what we're going to do is we're going to convert from a rational form to a radical form. And then we're going to evaluate, because it might be a little bit easier to evaluate when we see it in radical form. So 64 to the power of 1/2. If I want to write this in radical form, the 2 becomes the sign in front of the root. So the second root, or the square root of 64, all to the power of 1. Now that's a little bit messy, so let's simplify it a bit. I don't need to write this exponent of 1. And I also don't need to write the 2 in front because no value there implies that it's the square root. So I can just write the square root of 64, which evaluates into 8. So I've written it in radical form. And then I've evaluated. So I've written it in radical form, and then I've evaluated it. In the next example, -8 to the power of 1/3. So the 3 goes in front of the root. So this is telling me it's the third root, or the cubed root, of -8. I could put to the power of 1. That doesn't really change anything. So I now have it in radical form. Now I can evaluate this even though there's a negative there. I am able to evaluate other roots if there's a negative. It's the square root as well as the fourth root. So any even roots, I can't have a negative base there. But if it's an odd root, I can, because what this is saying is I'm looking for a number where if I multiply it by itself 3 times, it gives me -8. And because I'm multiplying by an odd number of negatives works out to a negative. So I can have a negative here, in which case the cubed root of negative 8 is actually negative 2. Because, just as an aside, negative 2 times negative 2 times negative 2 equals negative 8. And this only works when you have odd numbers of bases. Right? So we have 3 bases, odd number, so we can have a negative answer and take the root of it, or the cubed root in this case. C, 27 to the power of negative 2 over 3. Now in this case, if I want to turn it into a radical, my best bet is to turn it into a positive exponent. So to turn it into a positive exponent, I need to flip my base, so it becomes 1 over 27 to the power of 2 over 3. In this case, now I can simplify that base, or I can simplify that denominator and turn it into a radical. So in this case, it becomes 1 over the cubed root of 27 all squared. I can simplify this or evaluate it. So this is the radical form. Looks a little bit confusing, but it is the radical form. We have a root there. I can simplify this because I can take the cubed root of 27, which is 3, and I can square that. So the cubed root of 27 is 3. That answer is squared. 3 squared is 9. So my final evaluated answer is 1 over 9. Lastly, 243 to the power of 3 over 5. So that 5, again, becomes the root. So it's the 5th root of 243, all to the power of 3. I can then evaluate this by finding that root. Now, depending on your calculator, you want to look for a button that looks something like that, because that will give us the option to plug in a value for the specific root. So the 5th root of 243 is 3. That is raised to the power of 3. 3 to the power of 3 is 27. So it is easier to work with when dealing with radicals. It's a little bit easier to kind of do with almost even without a calculator if you're familiar with your multiples of 3 and 2 and so on, like, or not multiples, but exponents, right? 3 times 3, or 3 squared, 3 cubed, and so on. But that is our evaluated form from radicals. So let's just go through and simplify each of the following and then write it with a positive exponent. So we're just going to incorporate the power laws working with rational exponents. Now we don't want to convert them to radicals yet. If anything, similar to when we're dealing with positive exponents, we're going to only convert to radicals, 1 if it asks us to, and 2 at the very end when we have a single power. Until then, work through the power laws with the fractions. So in this case, x to the power of 1/3 is going to stay the same. The second power, it's a power of a power. So we have x to the power of 1/3 multiplied by x to the power of 5 to the power of negative 3 over 6, or negative 1/2. So this simplifies to x to the power of, and because it's a power of a power, we multiply, so negative 15 over 6. I can simplify this a bit. X to the power of 1 over 3 multiplied by x to the power of negative, we have 5 over 3. Now we need to convert, or not convert, sorry. Now we need to evaluate, or not evaluate, sorry. We still need to simplify. I'm getting ahead of myself. We still need to simplify. I'm just focusing on that power of a power. So multiply, so 15, divide both sides by 3. Oops, it's actually negative 5 over 2. I knew there was something off there. So negative, or x to the power of 1/3, which hasn't changed, multiplied by x to the power of negative 5 over 2. When I'm adding or multiplying powers with the same base, I have to add the exponents. So in this case, I need to add 1/3 plus negative 5 over 2. When we're adding fractions, we want to ensure that they have the same denominator. So in order to get the same denominator, we need to come up with equivalent fractions. In this case, 1/3 and negative 5 over 2, common denominator is 6. So 2 over 6 plus negative 15 over 6, back where we started. Now I can work with this. Now I can add these values together. And I would get x to the power of, this simplifies to, negative 13 over 6. Finally, I want it into a positive exponent, so this becomes 1 over x to the power of 13 over 6. I could turn it into a radical if I wanted to, the 6th root of x to the power of 13, but it's only asking for positive exponents. So the main thing here, let me actually just adjust this so we can see it fully. Over x to the power of 13 over 6. So the main thing is we're just working with rational exponents. So really we're just working with fractions. For b, similar idea, except we're dividing two powers in the end. We're going to simplify the top first. So 3 to the power of 1 over 4 times, or to the power of negative 2. This is a power of a power. So I'm multiplying. So 1/4 multiplied by negative 2 is negative 2/4 over 3 to the power of 5/12. Now I am subtracting my exponents next because I am dividing two powers. When I'm dividing two powers, similar to adding, or when I'm dividing fraction or subtracting fractions, similar to adding fractions, I need a common denominator. So the common denominator would be 12, so I can multiply the first fraction, everything by 3. So negative 6 over 12 minus 5 over 12 is what it's going to work out to. And this works out to negative 11 over 12. So I've subtracted my exponents, so that means then this simplified expression is 3 to the power of negative 11 over 12. I do want it with a positive exponent, so I do have to flip my base, so 1 over 3 to the power of 1, or to the power of 11 over 12. And again, I could convert it to a radical if I wanted to. Last two examples. So now we're given a radical and a rational exponent. So we do have to do a little bit of conversion. So let's convert this to a rational form, because in that way we can use our power laws. So for the 4th root of 16 to the power of 3 works out to 16 to the power of 3/4. That's multiplying 16 to the power of negative 1 over 4. Multiplying powers with the same base, I add. Nothing special here because they already have the same base. So 3/4 plus a negative 1/4 is equal to 2/4. So I get 16 to the power of 2 over 4. I can simplify that fraction, 16 to the power of a half, which I could reduce to the square root of 16 in radical form if I needed to. The last example, so this is a bit of a messy one. It looks messy, but it's actually quite simple compared to some of the other ones we've dealt with. So b to the power of negative 3 over 8 to the power of 4 to the power of 2 over 3. So it's a power of a power of a power. So when we're dealing with powers of a power, we are multiplying. And multiplying fractions tends to be very easy. Negative 3 over 8 multiplied by 4 multiplied by 2 over 3. So when we're multiplying fractions, we just multiply the numerators and multiply the denominators. A whole number is over 1. So negative 3 times 4 is negative 12, times 2 is negative 24, over 8 times 1, which is 8, times 3, which is 24. So this actually simplifies negative 24 over 24 to negative 1. So this means that this entire power simplifies to b to the power of negative 1, which is the same as saying 1 over b. We could put positive 1 there, but really that doesn't change anything. So looks complicated, but it's actually probably one of the easier ones. And the big thing from this lesson is just dealing with rational exponents in the power laws that we've previously looked at. Nothing changes, it's still the same idea. And then we've also looked at how to convert between radical and rational forms.